Hello, and today we are looking at the Earth's atmosphere, so the gases that are in the Earth's atmosphere and how that has changed since the Earth was first formed to now. So, this is the composition of the atmosphere today. It's been like this for about 200 million years, roughly the same percentages of each of the gases. So it's been quite stable for that time. You'll see the biggest proportion of gas is nitrogen, and that makes up around 80%, which is about 4/5. And then the next biggest amount of gas is oxygen, which makes up about 20%. And then the tiny little slither of about 1% is all the other gases. So that's including carbon dioxide, water vapor, and the noble gases like argon and xenon and things like that. Okay. So obviously this is a pie chart. So for those that want to know exactly the numbers that I've used on that pie chart, because I know there's probably some of you, I've used 78% for nitrogen, 21% for oxygen, 0.04% carbon dioxide, and 0.96% other gases. Okay, but you just need to know it's about 80% nitrogen, 20% oxygen, and the rest is carbon dioxide and other gases. So as I said, it's been like this for about 200 million years, but the Earth is about 4.6 billion years old. And we know that the atmosphere has not always been in these proportions, but has changed in that time. The way that the atmosphere has changed over time is a theory. Now, a theory is something that we have a lot of evidence for, but we can't prove that it's true. Okay, so we have evidence, but we can't actually prove that it's true, but it's an idea that fits the evidence that we've got. So the Earth's early atmosphere and how it's changed is a theory. It has to be a theory because we cannot prove it with the evidence that we have, mainly because the time scale goes back 4.6 billion years. There was no life, certainly no people that long ago, and the Earth has changed a lot in that time. So even looking at rock evidence and things like that can only go back so many years. So this is an artist's depiction of what the Earth may have looked like 4.6 billion years ago. And at the time, it is thought that the main gas in the atmosphere was carbon dioxide, and that carbon dioxide made up the majority of the gas. Now, some of the evidence for that is actually looking at other planets. So if we look at the atmosphere of Venus and the atmosphere of Mars at the moment, we think that their atmospheres reflect what our atmosphere was like 4.6 billion years ago. So the atmosphere on Mars and Venus is very high in carbon dioxide, and therefore they're both quite hot planets, and that's what we think the Earth was like all those years ago. One of the reasons we think that as well is that there were lots of volcanoes covering the surface of the Earth, and those volcanoes would have been releasing all of that carbon dioxide. They also would have released a lot of water vapor, and the water vapor basically formed this blanket of steam around the Earth, and that blanket of steam condensed, and when it condensed, it fell as rain into oceans, and that is how the first oceans were formed. So here we go, here's a volcano, and that volcano is releasing huge amounts of carbon dioxide and water vapor into the atmosphere. As well as those two gases, we also have large amounts of nitrogen being released, so that is where our nitrogen in the atmosphere has come from, as well as small amounts of methane and ammonia as well. Okay, so those gases would have also been higher in the early atmosphere than they are today. And you'll see also the water vapour coming out as those clouds and then precipitating and forming the first oceans. So the oceans were obviously really important because you can't have life without water, and that water needs to be in liquid form for much of life to occur. But even before that, the oceans were playing an important part in starting to change the Earth's atmosphere. So carbon dioxide dissolves quite readily into water and produces carbonates. Those carbonates are solids, so very small precipitates. And those precipitates would sink to the bottom of the ocean and produce sediments, and those sediments layers would build up, and that is forming the first sedimentary rocks. So we are taking, or the oceans were taking, carbon dioxide out of the atmosphere. It was dissolving into the water, and it's the first step in reducing the amount of carbon dioxide in the atmosphere, making it more like how it is today. So the decrease of carbon dioxide is one of the biggest changes from the early atmosphere to today, but also the increase of oxygen is also a big change. Now, obviously, without oxygen, life as we know it just wouldn't exist, because oxygen is important for respiration. So this change was obviously very important. However, when life started out on Earth, there wasn't oxygen present, certainly not in any large quantity. So early life forms had to use other chemicals in order to release energy. So those early organisms were chemosynthetic bacteria, and they would use carbon dioxide, water, and other chemicals like hydrogen sulfide in order to produce their own sugars and other compounds. So this was the first step of life being formed and being able to make its own food. So the sugar would have been its own food. Some of that chemosynthetic bacteria began using light instead of hydrogen sulfide as an energy source for that reaction, and that would have given us our first photosynthetic bacteria. So chemosynthetic bacteria use chemicals in order to combine carbon dioxide and water to make sugars, but the first photosynthetic bacteria would have used light as the energy source to combine carbon dioxide and water to make the sugars. And it's the sugars that is the food. And once you've got organisms making their own food, that's really where life then began to explode. And lots and lots and lots of different life could be evolved. So that photosynthetic bacteria then led to the evolution of algae. So algae was one of those first types of microorganisms to use sunlight and carbon dioxide and water to produce oxygen and glucose, which it could then use in respiration. So it's the first time we've got oxygen now being produced. Obviously, this is photosynthesis. So a reminder there of the photosynthesis equation. Carbon dioxide plus water goes to glucose plus oxygen. And the balanced symbol equation, 6CO2 plus 6H2O goes to C6H12O6 plus 6O2. So algae were our very first photosynthesizing microorganisms, and they were integral for causing the amount of oxygen to start increasing. As more and more oxygen began being released, more and more complex plants could evolve, and that meant more and more oxygen could be released, which meant more and more complex plants could evolve. And so eventually you've got very, very high levels of oxygen, and therefore the ability for more complicated organisms, and that is where we then start getting our first animals. Now, algae first appeared about 2.7 billion years ago, and then it took another billion years for animals to then start to evolve. Okay, so we are talking very, very long time spans here. So the age of the Earth is about 4.6 billion years old. First algae was about 2.7 billion years ago, and then the first animals was more about 1.7 billion years ago. Okay, so we're talking very, very long times. So you can see in that diagram there, at the bottom you've got your earliest forms of life, cyanobacteria and a type of protozoan are thought to be the ancestors of all plants. And then as you move up the tree, as it looks like, you get your more and more complicated animals which have evolved. Okay, so you've got your algae, you've got red algae first, and then you've got your green plants and your green algae, and then you get land plants, and then things like mosses, which are quite simple, and then you get a lot more complicated with ferns, and then you go into like your conifers and your big trees and your flowering plants, and they're the more complicated ones, which would have evolved a lot later on. So having all of these photosynthesizing organisms, not only was the amount of oxygen therefore increasing, but as they were taking in carbon dioxide for photosynthesis, the amount of carbon dioxide from the atmosphere was therefore decreasing. So it was being used by those plants and algae to produce sugars, and then when the animals came along and were eating those plants and animals to gain those sugars, the carbon was then being passed through, and so it was then passing through the food chain into animals. So we've got carbon from the atmosphere now being locked into stores of plants and animals as well. So as our plants and animals are carbon stores, when those plants and animals died, and became buried under water and dirt and got compressed, lots of heat and pressure, they can eventually turn into fossil fuels. Okay, so mainly coal would have come from giant plants from about 300 million years ago, and when they died, then they obviously fell to the bottom of the ground and would have partly decomposed, but anything that didn't decompose would get buried and then compressed, and that's how you get your coal. Oil and gas tends to have been formed from ocean life, so sea plants and animals which were then buried on the ocean floor, covered by silt and sand, and then again heat and pressure would have then turned them into oil and gas. Okay, but whichever method, or from whatever they've come from, you've got life which has got carbon in it, dying, being compressed with lots of heat and pressure, and becoming a fossil fuel. So that fossil fuel will also contain carbon. So coal is mainly just pure carbon, and then oil will be our crude oil, so full of hydrocarbons, and gas like methane, for example, which is also a hydrocarbon. So obviously carbon dioxide was still being dissolved into oceans, so oceans were still present. Carbon dioxide would still have been dissolving into it, producing those carbonates to make sedimentary rocks. But now there's marine life. Okay, so that marine life is able to use those carbonates in the ocean and use it to its advantage, making coverings and shells. And so that's what a shell is. A shell is just a carbonate. When those animals then died, they would also sink to the bottom of the ocean, and their carbonate shells would also form those sediments and build up in sedimentary rock. And they would form specific rocks like chalk and limestone. So that diagram there, that photo is a microscopic image of chalk. So you can see that chalk under a very powerful microscope, you can actually see the sort of shell formations of the organisms that would have used them. So where the little indentations are, that would have been the sort of the fleshy part of the organism, and then you've got their shell around the outside. And they've sort of clustered into these little balls. And that is chalk. That is what it looks like. Very, very small shells, basically. So, just to summarise the key points from that. The atmosphere now is 80% nitrogen, 20% oxygen, and a small amount of other gases and water vapour. However, 4.6 billion years ago, it was mainly carbon dioxide and water vapour. And that was due to the large number of volcanoes, which also released nitrogen. We think it's similar to what Mars and Venus are like today, and the water vapour we know condensed to form oceans. We know that the atmosphere changed, and we think that carbon dioxide decreased due to it being dissolved into oceans, becoming sediments in rock, being used in photosynthesis, and being locked up in fossil fuels. And we know that oxygen increased, and we think that is due to the evolution of algae, which started to photosynthesize to release oxygen, and that led to the evolution of more complex plants, which led to more photosynthesis, and that cycle just continued until we had animals as well. Okay, so they are all the key parts to the Earth's atmosphere and how it has changed. Now, there is a link at the top of the slide, which you can type into YouTube, and it's a really, really nice visual video of how the atmosphere, well, how the Earth really has changed, including things like how the moon was formed. It's not very long. It goes into a little bit more detail than this and to what you need to know, but it's a really, really nice video. So if you've got the time, have a watch. Thank you very much.